Myself, Dr. Prabhakar Rapaka, working as an associate professor. My subject is Unlike CMOS IC design. I'm going to discuss about the Unit 1 Basic MOS Device Physics. In that, the general considerations and IV characteristics of MOS devices. So in this Unit 1 consists of our basic MOS device physics. First one is general considerations. They are MOSFET as a switch, MOSFET as a current source, MOSFET as a structure, MOS symbols. So these are the general considerations you can consider. Next one is MOS IV characteristics. In this we can discuss about the threshold voltage, derivations of IV characteristics, MOS transconductance effect. Next one is second order effects. Next one is MOS device models. Next one is FinFET and MOS device act as a capacitor. Single stage amplifiers applications. Single stage with the diode connected. Next to as a source follower, common source, common gate, common drain, MOS configurations. First one is general considerations of MOS device physics. There are three main general considerations. First, consider MOS symbols. So in these MOS symbols, with respect to the NMOS or PMOS, we can denote it as three different configurations. One is with respect to the bus. Here this MOS means metal oxide semiconductor field effect transistor. Here field effect transistor consists of three terminals. They are source, gate and drain. It includes the body effect. That's why you are considered substrate body. So that is represented here body. Now we can observe here this is the drain terminal and this one is gate terminal, this one is source terminal. Here we are representing NMOS and PMOS. Here majority charge carriers are NMOS electrons. In PMOS majority charge carriers are holes. Based on this, these are represented as PMOS and NMOS. In NMOS we are observing here current flow from the drain to the source. So that arrow direction here we are observed towards the source. That is the direction of the current. On the other hand, in PMOS, current flow from source to the drain. Here observed direction from the source. This is one type of the representation. And another also, NMOS can be represented here without noting any body. Here also without noting any body. So this is the NMOS and PMOS representation. Or with including the bubble in the PMOS and there is no bubble in the NMOS. So these are the different symbols represented MOS device. So this MOS is act as a switch. So second one is MOS act as a switch. So in this we can observe there are different conditions we can consider for the gate. If gate supply is 0, that means this is act as an open circuit in NMOS. And if gate is 1, then it acts as a short circuit in NMOS. In other hand, if gate is terminal is 0, then it acts as a short circuit. And if gate is 1, it acts as an open circuit in PMOS. So this is the significance of MOSFET as a switch. Next one is, third consideration is mass structure. The useful action of this device occurs in the substrate region under the gate oxide. So based on that, here mass structure is considered significantly. Here this is the basic MOSFET device internal structure. It contains here source, gate and drain terminals are here developed. Here N plus here we are getting the source terminal and drain terminals, and polysilicon from the polysilicon we can observe the gate terminal, and oxide layer is insulating layer between the gate oxide and substrate. So here this is a substrate, this is a gate source terminal, drain terminal, polysilicon, oxide layers. Next one is, here in structure we can observe the effective length between the source and here a drain that gives the channel length. So that is we are represented as a L effect, thus effective length between the source and drain. And the total length between the source and drain is called as L drawn. And here LD side diffusion here observed between the gate and drain terminals. So this length is indicates the side diffusions. These side diffusions areas are act as a PN junctions. So here this MOS structure you can observe there are 3 terminals. Here are 4 layers like source, gate, drain terminals we can develop from the layers. At the same time, substrate is considered as a one more layer. So this construction we can observe the basic consideration. So from this what we are observed, there are 3 considerations. One is MOS symbols, next MOS as a switch, next MOS structure. So in this MOS structure we can observe the side diffusions here that is S by D junction diodes act as a junction diodes. These are always provide the reverse biasing case when we are observing the basic operation of this structure. And also in MOS structure we can include here N well and P well sub constructions we can observe, because here we are generally consider for NMOS or PMOS in any CMOS technology we can consider as a common substrate. Suppose in common substrate we call it as either NMOS or PMOS. For example, it is a PMOS we can develop N well, and for NMOS we can develop P well. So both are NMOS and PMOS transistors are developed in common substrate. So such cases we are developed here well process. So this is well process is also called as a local substrate. Next one is threshold voltage are considered for before deriving the IV characteristics of a MOS device. We have to consider the threshold voltage levels. Here threshold voltage means at certain voltage the junction going to be take the conduction between the source to the drain, or if we are increasing the depletion width by applying power supply to the gate. Based on the gate supply, the current flow from drain to the source may be vary with respect to the gate supplies. At a certain voltage we are going to develop the proper channel between the source to the drain to flow maximum current flow from the drain to the source. So that particular voltage level is called threshold voltage. So that is we can observe here in the so here first one is we can observe figure A. So A is a MOSFET driven as a gate voltage. Here MOSFET gate voltage you can observe, suppose here P type of material, N type material, here N type material. Here gate we are applied gate supply, positive supply to the gate, and you can observe here the drain side positive supply. So this is one type of the threshold voltage representation. So in threshold voltage representation we are applied here gate voltage. Here gate voltage is positive voltage, and drain also you can observe positive supply. So then current flow from the drain to the source. So that is done by whenever we are applied positive supply to the gate voltage, here positive ions are developed in the substrate. So that is between the two N type of materials, and it is also between the source and here you can observe this is the source and drain. Now here negative ions, these are negative ions are developed due to the positive supply applied to the gate terminals. This is one representation, and another one is you can observe here this whenever we are applied positive supply to the gate, here gate to substrate, gate to here is polysilicon layer. Here gate is act as a developed from the polysilicon. So this polysilicon and silicon dioxide layer, in between these two layers the capacitance developed, that is called COX, gate oxide capacitance. So here that is you can observe in the so that is called inversion layer developed due to this capacitance between the source and drain. And from the silicon dioxide layer to the substrate, here developed one more capacitance, that is depletion capacitance. Depletion capacitance. We can observe the depletion region. So these two are capacitances developed between the drain, gate and silicon dioxide layer and substrate. So due to these concepts, here whenever we are applied positive supply to the gate, here electron ions or negative ions are developed between source and drain. At the same time, electrons are developed between source and drain. So that is called channel. Here we are observing the this is called channel developed. At certain voltage, at certain gate voltage, here the current move from drain to the source with the sufficient channel developed between the drain and source. So this sufficient voltage is called threshold voltage. So the formula for this threshold voltage we can represent with respect to the work function and depletion charge and capacitances. So that means the threshold voltage for NFET. NFET means N type of metal oxide semiconductor field effect transistor. We can observe that is also called as NFET. So which is defined as a gate voltage for which interface is as a much N type as substrate is P type. So that means you are considered the NFET. So in this NFET, substrate is considered as a P type. So in this case, we can observe the this is the threshold voltage formula, where pi of ms here threshold voltage VTH equal to pi ms plus 2 pi f plus q depletion by COX, where pi ms is the difference work function between the polysilicon gate and the silicon substrate. So that means here you can observe this is a polysilicon area and this is a silicon substrate area. So between these two, so the channel developed due to the certain voltage that is called VTH. This VTH is developed with respect to the here work function. Here you can observe work function done between the this polysilicon and substrate. That is called M pi F. That is called pi ms. Pi ms. And next one is you can observe QF is considered as a from the semiconductor reference here. Pi f is equal to kT by q or ln of n substrate by n intrinsic, where k indicates the Boltzmann constant and q is the charge of electron and n indicates the doping density of the substrate and Ni indicates the electron density under the silicon. And QDP indicates the depletion region charge of depletion region. And COX is the oxide capacitance per unit area. So according to the PN junction theory, here Q depletion is equal to here under root of 4Q epsilon Si mod pi f mod n substrate, where epsilon Si indicates the dielectric constant of silicon. Since QX appears very frequently in the device circuit calculations, so which helpful for the TOX is here thickness of the oxide layer that is approximately equal to the 20 angstroms, and COX is 17.25, and the value can be considered with respect to the oxide thickness. So this is about the threshold voltage. So your threshold voltage is typically adjusted by implantation of doping into channel area during the fabrication. That means this threshold voltage more affected on the operation of the mass devices. Let's say we are considered this improve the we are getting the sufficient threshold voltage to develop channel between the source to the drain. So for that case, we are adding some dopants to the substrate. Then it can easily develop the channel between the source to the drain. So for that, here the positive dopant can be added. Then here very easily we are generating the some voltage level which is VGS is greater than or equal to VTH. The gate to source voltage should be greater than VTH. So this is developed by adding positive material to the substrate. So that is called doping level increase to maintain the proper oxide interfacing. Next one is derivation of IV characteristics, current voltage characteristics of mass devices. If the mobile charge density along with the direction of the current is considered as a QD coulombs per meters, and the velocity of the charge is V meters per seconds, then the relationship between the the direction of current and velocity of the charge and can represented as I equal to QD into V. So for example, consider current carrying conductor direction shown in figure A. Next one is V meters. Here 1 second meter you can observe here. So in figure B, whenever current move from the one place to the other place in a conductor, the flow of current is can define as the rate of change of charge. So here charge is represented as QD, and the velocity of the electron is V. Then the relationship between I charge and velocity is equal to I equal to QD into V. So maybe it's considered as equation 1. Next one is consider charge density in the inversion layer. So here inversion layer developed due to the gate supply voltage. So here we are consider the there are two conditions. One is VD equals 0. Second one is VD is greater than 0. If VD equals 0 means you can observe here the charge density in the inversion layer is VD equal to 0. That means you can observe from this figure. Here both are VG here applied, source and drain both are grounded. That means VD is equal to 0. Another case is here it is actually the mirror. This is the mirror image. You can observe this is one area, this is another area. So the supply voltage at this area, supply voltage at this area is equal. This is one case. Another case is supply area, one case is different, and other side we are applied some voltage at the gate side. That is VD is greater than 0. So if both are equal, then this QD in terms of here width and COX and VGS minus VTH. So this is the QD equation. WCOX into VGS, the gate to source voltage minus VTH. Because here gate to source voltage is greater than always VTH, because we are adding some dopants to the substrate to develop the proper channel. So in that case, inversion layer developed. That charge density of inversion layer, you can observe QD equal to W. So this is considered as equation 2. And this is another case. So in this case, here we are applied some voltage, that is V of X. Here we can observe this is equation 3. Now suppose if you are considered there are two cases. One is VDS is greater than VGS minus threshold voltage. In this case, you are going to consider the current equation. ID equal to generally ID equal to QD into V. Substitute here QD and V. So according to the equation 2, here QD equal to, this is the equation, and V, and this is ID from the first equation. So this is the equation 1. Here derived equation for QD. Now substituted in equation 1. Then from these two conditions you have to apply. VD equal 0 one case, VD greater than one case. So this is the one equation. In this case, you can observe this is one equation 3, 4. This is equation 4, and apply the we have to find the derivative of this Vx. So now we have to apply the derivation with respect to the x on the both sides. Right is constant. You can observe this is the equation. Now apply integration on both sides with respect to dx. Then after simplification of this, integration for from v equal to 0 to the VDS constants. Here integrated with respect to the dx. And at the end, you can observe this is the final equation for our drain current, maximum drain current flow from the drain to the source. So in this case, here plotted the graphical representation between ID and VDS. So here VGS 1 minus VTH, this is one area, this is another representation, this is another representation. So from here to here, this one is indicate the deep triode region. So in this deep triode region, here VDS is less than VGS minus VTH. So that one indicates the ohmic region, resistance region or deep triode region. So this is a graphical representation between VGS and VDS and IDs. So this is considered the equation 6. So if you are applied VD greater than 2 times of VGS minus VTH, then we have, so this is the approximated current equation, diode current equation. So in this case, you can observe linear relationship between the VDS and ID. Thus, which is a path from the source to the drain represented by linear resistance equation. So from this current, we can observe the relationship between current to voltage and resistance. Generally, I is directly proportional to V directly proportional to I. V equal to I into R. From this, R equal to V by I. According to this one, you can represent this I is nothing but ID. Suppose V equal to 1. Then you can observe this is nothing but ID. Or V equal to 1. So this is, you can represent it as a source gate drain terminals. Here VGS and source to drain. So this is act as a resistance for the MOSFETs. So this is the equation 8. And other case is VD greater than or equal to VTH. So in this case, we can observe the different graphical representation between VDS and ID. So here the transistor is act as a saturation region. At that time, ID equal to, this is the equation. So this is the equation 9. So that means whenever we are consider this gate to substrate voltage difference VTH, here you can observe this is the electron channel. Here channel at certain time we are applied some this is the ground one, this is the positive supply, this is the positive supply. Then VDS is greater than VTH minus VGS minus VTH. At that time, here VDS is more positive. So if it is more positive means here this effect we can observe due to the VDS, and here at certain voltage, here there is no channel between source to drain. So this point is called pinch off. If you goes on increasing this one, here reduce the channel. So that is called, this area is called pinch off region. So here you may observe this is the pinch off point and this is the depletion region. This is the condition you can observe. So in that case, here this based on the supply, based on the dopant levels, here channel goes on increasing or decreasing. So this will give the special applications with respect to the here VDS and VGS and VTH. So in that case, here MOS transistor is active in saturation region. So if it is less than, it is worked in or deep or triode region. So in this portion, you can observe this is a pinch off area, threshold area. So at this point, this transistor is act as a current source. MOSFET act as a current source. That means with respect to the channel, the current can be controlled. Next one is transconductance. If VDS is greater than VGS minus VTH, then the transconductance is defined as the current by voltage. Actually, it is dou ID by dou VGS at VDS constant. So this one indicates the transconductance. Substituted here ID and VGS values. Then we can observe this is the equation, and by simplifying this, apply here W by L VGS minus VTH you can apply here, then ID, then it can represent as a actual final transconductance. This you can consider the equation. So VGS equal to V minus VTH. So this is one graphical representation, and W by L constant. Okay, this is ID constant. So these three types of graphs you can observe from this VDS greater than VGS minus VTH.